this chapter, we're going to look at topics related to measurement. In this lesson, we're going to look at linear scale factor.
Okay, everybody. So in this lesson, we're going to take a look at linear scale factor. Okay, and scale factor here, and I've circled that there. Scale factor is just another way of thinking proportionally. Proportional reasoning shows up all sorts of different places. It's really quite prevalent. In fact, I suspect for a lot of us, as we're kind of out and about doing our daily lives here, we don't even realize when we're doing proportional reasoning, but it's there. It kind of happens here. So one way of describing the enlargement or reduction of an object proportionally, you ask yourself, by what factor do we need to multiply the original to get the model or the new? Okay, to go from like a small image to a large image, how much bigger is it? How much bigger did the side lengths get here? And notice that we're always comparing like dimensions. And what I mean by that is we're going to compare width with width, height with height, and so on. Okay, because that's the only way you can get a really clear idea of how the object is being either expanded or reduced there. If you compare basically apples to apples. So as an example here, as we work through this page here, ask yourself, by what factor do I need to multiply the original width by to get the new width? And so that's how we get our scale factor. We take our model and we divide by our original here. So let's just zoom in on this, because this is really key here. Or we take the new length, the new linear length here, and divide it by the old one. Okay? So, for example, let's start off with a rectangle A. So here we go. It's 3 centimeters by 2 centimeters. And in fact, that might even be true. Hold on. Oh, not quite. Really close, though. So we can enlarge or reduce that triangle. Anytime you've got a scale factor that's greater than 1, the result will be an enlargement. And that actually makes perfect sense when you think about it, because if our ratio here is the new length to the old length, if the new is larger than the old, then this ratio here will be greater than 1. On the other hand, if the scale factor is between 0 and 1, it will result in a reduction. And by the same reason, if that new length is smaller than the other one, then that fraction there, that scale factor, is going to be less than 1. So here we go. So if we went from, remember, 3 and 2 to 6 and 4, okay, so remember, our old one was in here somewhere, and this was 3 and this was 2, and so this has gotten bigger, this has gotten bigger here. So the width scale factor, the model, the new one is 4, the original was 2. That's by a scale factor of 2. Now, sometimes you want to check everything here, because not all the time does everything get enlarged by the same amount in all directions. Sometimes we stretch it out even a little bit. So let's take a look at the length here. The new one is 6, the original one was 3. No, in both directions it's 2. It's been multiplied by a factor of 2. So we haven't even changed the shape here. But you could do that. Like, I could just take the object here and stretch it out horizontally and leave it the same height vertically, which distorts the image. But in this case here, there would have been no distortion, because it's the same amount in both directions. Likewise here, now I'm drawing this bigger just to make so it's a little bit clear here. My original was 3 centimeters and by 2 centimeters, and now it's come in. And so what we've got here is our model, the new one here. The new width is 1, the old width was 2. And so, I mean, that's my scale factor all on its own there, 1 over 2. The length scale factor, the model here is 1.5 and the original was 3, and again, that's a half. So there's been no distortion to the image, it's just gotten smaller by a factor of a half. Now, one of the things to remember here, and it has confused a lot of people here, is what has changed here are the linear the linear distances here. The area of the image has changed by a substantially different margin here, by a different factor, okay? But the length here, this length here is now twice as long when I change it. This length here is twice as long. But the area is quite a bit larger than that. So you don't want to confuse the two. You really want to try really hard when you look at this image here to make sure that if I'm talking about a linear scale factor, that it's just the lengths of the sides that I'm comparing and not the area of the whole object. Okay, so before we get into an example here, just Just to really quickly summarize here, so a linear scale factor describes the enlargement or reduction in linear measurements. This is what I was trying to get at just a couple seconds ago, linear measurements. Okay, so length, width, perimeter, circumference, not area. Okay, this is not how we describe area here. And it can also be described as a ratio, a rational number, so a fraction, like A over B. Ratio would be like A to B. Or as a percent, right? We just convert the A over B into a decimal and then a percent. So now let's take a quick look at this example here. What is the linear scale factor of a rectangle C expressed as a rate, a fraction, or a percent here? So let's take a quick look. Down here. This was C. Okay, this was C as compared to the original one, A here. That's what they're asking for. Well, as a ratio, we already figured out here that I could reduce that down here. So for example, my model was 6 and when the original was 3. I'm just taking the lengths here, okay? Reduce that down and I got 2 to 1. So the fraction way of, of discussing that would be as if to say here 6 over 3, which would become 2 over 1, okay, which we know is just going to be 2. But then as a percentage, okay, 2 over 1 is 2 here. Remember, what you would do then is you would take that fraction that multiply by 100. That gives us 200%. Okay, when you looking at that scale factor. I hope that makes sense. Okay, the 2 to 1, 2 when written as a fraction, or 200% when you multiply by 100 to convert that into a percent. So in this question right here, it says determine the scale factor that will transform P, diagram P, into diagram Q, and give your answer as a ratio, rational number, percent here. Okay, let's compare these two. So let's go like horizontally here in terms of its dimensions. So in P, this is 1, 2, 3, 4, and for Q, this is 1, 2, 3. So right off the bat here, when I look at new as compared to old, this is 3 to 4. Now I'm not 100% sure that that's true in both directions. So let's take a look at the height here. 1, 2, 3, 4. 1, 2, 3, and that is true. So it's good in both directions there, so I can run with that. So as a ratio, I would write that as 3 to 4. Okay. As a rational number, that would be 3 over 4, which when it says here, or a terminating decimal, I know that that's 0.75. So right here is where I probably see most clearly that this is going to be a reduction. I mean, I can tell by looking at the diagram that Q is smaller. But if all I've got is the scale factor here, or the proportion, because I know that this is less than 1, I know this is a reduction. And then I can convert that 0.75 into a percent by simply multiplying by 100 to get 75%. So the new diagram, the new triangle, is 75% the length and width of the original. Okay, so this question says that triangle A primed, B primed, C primed, which over here is this little guy right here, has been enlarged to give triangle ABC. Okay, what is the scale factor for the enlargement? Okay, well, let's take a quick look at this. So to get a sense of that, what I want to do is figure out, well, let's look at my old and compare that to my new. So my old is 2 units across. My new is 1, 2, 3, 4, 5, 6 across. So right now, if I go new to old, that's going to be 6 to 2. Now, I know that is going to reduce down to 3 to 1 here, and that's good. I just want to make sure that that's true for both dimensions here. So I've got 1 is my height here, okay, and 3 is my height of this triangle over here. So that works in both directions here. So there's my scale factor for the enlargement. Now, the second question says, what if ABC had been reduced to give A prime, B prime, C prime? What would the scale factor be? Well, the nice thing about this relationship here is that all I have to do here, basically what I'm saying here is that my new and my old are flipping. Okay? So now, to go from new to old, what happens here is the new has a width of 2 and the old has a width of 6. And that gets reduced to 1/3. So really what happens here is I just take the scale factor and I reciprocate it. Okay, so for this next question, and I like this question by the way, it says consider the pair of rectangles to the right here. Okay, so here we go. Now just to make sure that you can see them here. This is 10 by 8 and 30 by x. Okay, So now we're going to assume that the one is just an enlargement of the other here. So determine the perimeter of the larger rectangle without calculating x. Okay. Okay, well, let's take a quick look at this. First of all, let's figure out what the linear scale factor is to go from the small one to the large one here. So our new length here is going to be 30. Our old length is going to be 10. So if we get our little new to old here, okay, that is going to be 30 over 10 or 3. So we know that in terms of the length, okay, and that this is going to be representative of all of the different dimensions here, the linear dimensions. It's going to be 3 times bigger. Now that means that if this holds, okay, if this holds for the length, this is going to hold for the perimeter as well, for the width and the perimeter as well here. So we can figure out the perimeter. Okay, we can figure out the perimeter of the old one. This is going to be 10. This is 8. So I know that 10 and 8 for these two right here is going to be 18. But I also know that this is going to be 10 and this is going to be 8. So it's going to be 18 plus 18. So it's going to be 36. So our perimeter here, 18 plus 18, is going to be 36 centimeters. Now, I know that our scale factor here is going to be 3 to 1. So we're going to take 36 centimeters. We're going to multiply that by 3 to 1. Okay, and 36 here multiplied by 3 is going to be 108 centimeters. So this is going to be the new perimeter. Oops. The new perimeter, 108 centimeters. I didn't even have to calculate what the side length was. Now, the next part of this question is going to be clearly to calculate that side length, and then I can use that to verify that I did this correctly here. Well, in this case, I already know that the scale factor is 3, that the new one is 3 times as large. So I'm going to take the old width, and I'm going to multiply that by 3 over 1 to get the new width, 24 centimeters. Now, I'm going to just double check here. Does this match up with my new perimeter? Does my new perimeter equal that 108 that I just figured out here? So it's going to be 2 times 30 plus 24. Well, it's going to be 2 times 54, and yeah, that works out to be 108 centimeters. So yeah, that's good. I feel quite confident about the work that we did just a couple seconds ago. So this question says, consider the rectangular prism to the left, to the right. Oops. This one right here. Let's take a good look at it. That's 3 by 4 by 5. Okay. Now what does it say? What are the new dimensions after the prism has been scaled by a factor of 10? Is this an enlargement or a reduction? Now, before I look at it at all or do any kind of math here, I know this is an enlargement. Okay? The scale factor is larger than 1. Okay, that's all I needed to know here. Now, let's take a look at the dimensions here. So let's take a look at the, let's say the length. Okay, so the length, what I'm going to do is I'm going to take that 4 centimeters, I'm going to multiply it by the scale factor, which is like 10 over 1. That's going to end up being 40 centimeters. The width, at 3 centimeters, same thing, because it shouldn't matter which direction I go. Okay, a linear scale, a linear distance here is going to be scaled by the same factor. And then our height here at 5 centimeters multiplied by 10 over 1 is going to be 50 centimeters. That's the new one. Okay, good. So now it says, what are the new dimensions after being scaled by a factor of 2/5? Is this an enlargement or a reduction? Okay, so 2/5, I know right away this is going to be a reduction. Now, maybe you can't tell by looking at that right away here, but if we switch to a ratio, 2 to 5 becomes 2/5, okay, which is less than 1. As soon as it's less than 1, I know that that's going to end up being a reduction here. So let's take a look at what the dimensions would be. So my length at 4 centimeters, I'm going to now multiply this by 2/5. It's just easier to do it this way. And that is going to end up becoming 8/5 of a centimeter. Now please, this is a good opportunity. Just let's talk about this. 4 times 2/5 does not become 8 over 20. Please don't do that. You do not distribute this number to the numerator and denominator. Okay, this is like 4 over 1 when it's written like this, and so the numerators get multiplied together, and then so do the denominators. Don't distribute that 4 to the numerator and denominator. Our width was 3 centimeters. It gets multiplied by 2/5, and so that's going to end up being 6/5 of a centimeter. And then finally our height, which was 5 centimeters, gets multiplied by 2/5. Now, this is going to end up becoming 10/5 of a centimeter. But 10/5, you'd never leave it like that. I mean, it makes way more sense just to simply write that as 2 centimeters. And those are your new dimensions. Okay, now we're going to look at scale diagrams here. Like it says here, often a scale will be used in diagrams that represent real-life things. Okay, like you look at a book or online, and you'll get a picture, let's say, of an insect, but it'll give you a scale because usually those are blown up quite a bit here. So things like maps, figurines, drawings, and whatever. So generally, in these circumstances, the units are different to begin with. So oftentimes you'll see scales that will be like a centimeter here will refer to kilometers on the map, or a centimeter here is going to refer to like micrometers or whatever the scale happens to be. But we're using different units. Normally, it used to be the case that we really wouldn't talk about it like that you'd have to convert to all the same units. There was an emphasis that they had to be the same, but it works even if the units aren't the same. Okay, as long as you're describing the same, like, when I say unit, what I mean is dimension. So length to length, width to width sort of thing. So the scale can be given in the following ways. It could be a word or a description. It can be a rate, where you've got different units, because you can scale that back. It could be just a ratio, usually with the same units. Okay, so you'd have to convert. Or as a line graph scale, which you sometimes get here. So just an example here. So 1 centimeter represents 0.5 meters, right? Or 1 centimeter per meter, kind of as a rate, 1 centimeter per 0.5 meters here. Or as a ratio. Now, when you write it like this, like it says here, remember you basically want them to be the same units. Okay, so that you're comparing apples to apples there. It's a lot clearer. Or you give it like this, and this is the one that you're probably most familiar with on maps there, okay? So this scale indicates that a measure of 1 centimeter on the diagram represents 0.5 meters in real life. Okay, so that distance right there, half a centimeter, is supposed to be interpreted as 0.5 of a meter. So, and I'm hoping that you've seen that sort of thing before. If you've looked at like Google Maps, they have that kind of that scale in the corner there. Anyway, let's take a look at some examples. Okay, so in this question we read, Logan measured a house and its lot and made a scale drawing. The backyard is 6 centimeters wide in the drawing. The actual yard is 24 meters wide. What scale did Logan use for his drawing? Yeah, okay, so what he's done here is we know that 6 centimeters represents 24 meters. Okay, now we can play with that just a little bit, okay, by simplifying that down a little bit, because we know then that every 6 centimeters is going to be 24 meters, but there's a common factor there, which means every centimeter, 1 centimeter, represents 4 meters. And that's the scale that he's using there. Now we can write this in different forms clearly. Okay, we could make that 1 centimeter over 4 meter, whoops, that's not what I meant. 4 meters. Okay, if we wanted to write this as a ratio, as was indicated above here, we probably want to convert that to same units here. So instead of being 1 centimeter to 4 meters, what we probably want to do is make that 1 centimeter and make this 400 centimeters. Okay, so 1 to 400. So for every 1 unit here, in actuality, it's 400 times bigger. And in some ways, this is a lot clearer. Okay, here I really got to think about the conversion Here, it's clear. This is 400 times larger than what I'm starting with. Okay, here we go. At the museum, Melanie sat down to draw a dinosaur exhibit to scale. In the drawing, the length of the dinosaur is 4.5 inches and the height of the dinosaur is 3.75 inches. The actual height of the exhibit is 15 feet. So what scale factor did Melanie use? Okay, so we're dealing with a height of 3.75 inches. Okay, represents 15 feet. Okay, well, what we could do is divide both of those, okay, by 3.75 to kind of reduce that down. Now, I'm only doing this because it actually works out relatively nicely. So what this means here is that 1 inch represents 4 feet. Okay, so we might write 1 inch over 4 feet, or we might write 1 inch to 4 feet, or what I like a little bit better here, we might use that scale ratio where we get rid of the units, make sure the units are the same here. So 1 inch, and actually, sorry, I wouldn't use the units there, because as long as the units are the same, it doesn't really matter what the units are. It's the comparison between them that's actually important here. No matter what units you get, this ratio will be the same here. But if 1 inch is 4 feet, how many inches is that 4 feet? Well, each foot is 12 inches, so 4 times 12 is going to be 48. So basically that dinosaur is 48 times the height as her diagram. And in fact, it doesn't matter what unit she chooses to measure on that diagram. In actuality, that dinosaur would be 48 times larger. So now, over here, what is the actual length of the dinosaur? See, I like using this right now, because if we start with 4.5 inches, what I can do is because now I'm going, this is representing the reduction here, right? We reduced it to get the diagram. Well, now I want to go the other way, and so I'm going to flip this. Instead of it being 1 over 48, I'm going to flip this over and make this 48 over 1. Now, 4.5 times 48 is 216 inches. Now, is that useful to me? Well, not really. And the reason why it's not terribly useful to me is because for most of us, our familiarity with the imperial system might be just a little bit weak here. In this particular case, it might have been better to actually say, okay, 4.5 inches, and then use that other comparison there, 4 feet to 1 inch. And here, the inches will cancel. See, and now I really do need to use the units here, because in this case, I want my inches to cancel. Here it didn't matter, because all this was going to do was change the number of inches. Here there's a bit of a conversion. And so 4.5 now multiplied by 4, this is 18 feet. Okay, that actually communicates a little bit more to me, because I have a better sense of how big a foot is. I mean, I know what an inch is, but in my mind, to kind of conceptualize 216 inches, I'm not clear on what that is. But 18 feet, I have a much better idea of what that means.